Okay, I think we will go ahead and get started here. Dr. Gay is sort of presenting remotely, so I think he'll have me go on to the next slides when he's ready. If you have any questions for him during the talk, please just go ahead and hold on to them till the end. You can type them into the chat window or ask verbally once his talk is over if he's got some time for questions. Otherwise, I will hand it off to Dr. Gay now. Thank you again so much for everyone for joining us.
And thank you, John, and thank you all for your time today. I'm speaking from a train station in New York and trying to find a spot without any background noise, but from time to time it's likely there will be some announcements, and I'll try and speak over that. John, can you hear me okay at the moment?
Yes,
Hello?
loud and clear.
Okay, great. So what I wanted to cover today basically is a general overview of solar. If you could go to the next slide, please. One of the key points that I wanted to make is that the rate of change that's happening in solar is very rapid. And that rate of change is something that is a key messaging element that we want to try to deliver to the public in general, because the tendency is to think that the way things are at one point in time will simply be incremental as time goes by. To make this point, this is a slide I borrowed from Martin Green. He has a slide here which shows New York City in Easter of 1900, and there's one automobile on that street. And on the next slide, we look at New York City 13 years later, and if you click again, there's one horse and buggy on that street. The speed of change when we see a technology merge like solar is merging, it catches many people by surprise. On the next slide, what I wanted to cover here is a little bit of the history of the silicon solar cell, just for some context. It was originally invented by Russell Ohl in 1940, and part of the reason for showing this slide is to give us all a calibration on how fast our technology does change or how fast it doesn't change. Ohl did this work while at Bell Labs. The sample that's shown in this photo is an actual cell that he made and is on display now at the Smithsonian, which is a solar exhibit that opened up in November. So over the course of the coming year, if any of you happen to have the chance to make a trip to DC, we'd love to see you, the solar group at DOE, but you may enjoy bringing your family to see the samples that are on display in the Museum of Natural History. On the next slide, not a whole lot happened between 1940 and January of 1954, but in January of 54, the Albuquerque Journal and then subsequently a number of other newspapers carried an article highlighting that David Sarnoff, who was at the time chairman of RCA, that the solar cells had been discovered as a way of basically converting beta rays or decay particles from nuclear waste materials into electricity. And that sparked the interest. On the next page, you'll see an excerpt from Bell Labs' response, which included publishing in the New York Times in April of that year. So a few months later, piqued by RCA's announcement of what they had done with silicon, the work that was going on at Bell Labs, it had largely been pursued by the Army Signal Corps. Hans Ziegler Werner von Braun were both folks who found a place here in the U.S. after World War II, coming from Germany, and Ziegler led the Signal Corps effort that funded a lot of the work that was underway at RCA. And the cell shown in the photograph there is a all-back contact cell, also on display at the Smithsonian. And part of what made this sort of contest relevant here is that once competition began, a lot of progress started to happen with the technology. On the next slide, the patent issued to Chapin, Fuller, and Pearson shows the cross-section of that roughly 1 centimeter diameter crystal cell in the photo before. The ingot was sliced lengthwise into a long thin slab, and a wraparound contact cell made on N-type silicon. And as all of you likely know today, P-type is the most common base material with an N-type diffusion, phosphorus diffusion on a boron-doped base wafer. Cells at that point in 1954 were about 6% efficient. The display at the Smithsonian actually has a small panel that was made with cells from the space program, and several of which also link back to this original work. And you can use the flashlight on your cell phone to illuminate the little panel in the display and see the meter show the output. The next slide. What really moved things along was the Soviets launching Sputnik in October of 1957. And the U.S. then embarked upon a crash program to launch its own satellite. And this satellite that you can see in the photo here is of Vanguard 1, and that was launched in March of '58. It's got those back contact cells on the periphery or the circumference of the satellite, and it's used to recharge a battery. The original Soviet satellite just had a battery without the ability to be recharged. And you can see that this was all 1/100th of a watt of power running this small satellite. One of the anecdotes that I like referencing here to reinforce this message about the speed of change that now starts to pick up with the space program is that in 1945, the provost at MIT made a declaration that there would never be a rocket that would travel more than 3,000 miles. 12 years later, in 1957, is when the Soviets launched the Sputnik satellite. And 12 years after that, 1969, is when man walked on the moon. So the speed of change that is inherent in the space program is one kind of reference that might be helpful for setting context here about how fast solar is changing. The next slide. This shows cells from the 1970s, and it's a comparison of what happens with improving efficiency and being able to reduce the number of, or the amount of area required for a given number of watts. So on the left-hand side is a small circuit of 2 by 2 centimeter cells, little bus bar across the top of each cell with grid lines, and the cells are soldered together and shingled together. The violet cell is a shallow junction. So as diffusions came under greater control, being able to reduce the phosphorus doped region from roughly half a micron to 0.2 or 0.15 of a micron in thickness, The short wavelength response, which is especially important in space, vastly improved, and you could eliminate 3 of the conventional cells, as they're called on the left-hand side. By about 1975, the ability to form texturized surfaces on 100-oriented silicon started to find its way into production of space cells, and that further enabled broadband trapping of light for those cells. Next slide. And in the time frame of 1973 to 74 was when the first oil embargo took place. 74 was when I got into solar. All of the A students at that time became nuclear engineers, and being a slacker I decided I'd try this solar field as something that might have a long shot at being able to help us with our energy self-reliance. And when I joined, initially I went to work at Spectralab making space cells, and one of the ground stations that NASA operated, they have basically 3 major sites around the globe, one in Goldstone, California, one in near Canberra in Australia, and one in Nigeria. And for the site in Nigeria, it was actually a isolated rural location without any electricity. NASA, Lewis as it was called at the time and now called the Glenn Research Center, gave us a contract at Spectralab to work with techniques that might enable lowering the cost. And by 1976, 1977, a typical single crystal diameter was about 2 inches, and these are a couple of 2-inch cells, one which basically has a thin layer of metallization deposited in vacuum and then plated up with solder in order to carry the current to the edges of the cell. And we had begun to experiment with lower cost metallization using screen printing, essentially the same thing that's used to make about 65 gigawatts of solar today is springboards from this time period when NASA wanted to be able to return back to that village in Nigeria some electricity that could be used for rice husking. So we began to make small modules with screen printed contacts and replaced the higher quality evaporated TiO2 or tantalum pentoxide AR coatings with atmospheric pressure CVD coatings, basically using titanium isopropoxide and methanol in a furnace that had ambient air in it. On the next slide, one of the most important things that distinguishes solar and wind is that they are manufactured energy sources, and all manufactured technologies follow a learning curve, a progress curve. In the case of transistors, for every cumulative doubling of production output, the costs have declined by about 30%. And in the case of solar, for every cumulative doubling of output, the costs have declined by about 20%. And that history of that 20% cost reduction for every cumulative doubling has followed us all the way back in time to this very first plot of what might happen if the government was involved in helping scale alternative sources of energy. And this is a hand-drawn chart that Gene Ralph made. Gene originally started as an engineer at Hoffman Semiconductor, which was the first company to start commercializing solar cells, and then was one of the co-founders of Heliotech, which then merged together to form Spectralab. And Gene plotted the cost of space cells and the sensitivity to what volume of demand was associated with each of the satellite projects, and made a rough estimate of how much costs could come down if there were markets for solar. That chart is really the godfather to all of our learning curve charts that we can point to for how the cost of solar have declined and continue to decline, and will decline as a result not just of economies of scale and improved logistics, but also as a result of making efficiency, innovations in efficiency, and just as importantly, identifying reliability attributes. There are modules now in the field today that I was involved in making about 40 years ago. Some of them are out at Natural Bridges National Monument in Utah, and they have the same output power today as when we originally made them. They weren't hugely efficient. They were about 9% efficient modules. But there's an existence proof that people can now reference and have confidence in the reliability of what we're making. On the next slide, this is a plot of that 20% learning curve. And over time, one of the major benefits for our industry has been that there's been a market as the costs have come down with reasonable elasticity. That is, once you get to a certain price point, you're able to increase the number of customers. So after space, most of the markets tended to be power line-of-sight microwave repeaters on mountaintops. So our early customers would be in places like Papua New Guinea, where the government of Australia Telecom and Wireless, was enabling the introduction of microwave repeaters for communication. That market allowed us to increase the amount of product we made that allowed for us to follow this learning curve here. Rural applications, then competing with diesel generators began to pick up, and perhaps the biggest innovation in the organization I was working at this time in the early 1980s, in 1977, at the time of the second oil embargo, Atlantic Richfield decided that it wanted to diversify into high technology areas, and I was hired to be the director of research and engineering and help set up the first and lead the manufacturing plant. And by 1980, we had a grand celebration at the end of the year because we managed to produce 1 megawatt in that year. Today, most fabs run producing a megawatt before lunch. So the scaling has really taken off, but it's still that same screen-printed contact system and pretty much the packaging system of tempered glass front, ethylene vinyl acetate, and a fluorinated polymer like Tedlar or a backsheet on the module. And we were able to then begin servicing rural markets where we were competing, as I mentioned, with diesel gensets. Today, the cost of power from diesel gensets is, perhaps in the best case, we could reference the price of electricity in Hawaii, which is around 40 cents a kilowatt hour. Solar is easily cost competitive when competing with gensets. But what I was starting to say is in the early 80s, the biggest innovation was in marketing. And we looked at Caterpillar for a reference on how to service markets in isolated areas with a capital good and be able to service that capital good. And Caterpillar had a two-step distributor dealer network. And so we copied that distributor dealer model for training our installers who would be certified, and we'd help them set up their businesses in rural communities or in urban areas adjacent to rural areas. And many of those early adopters of solar still are running their businesses, have scaled their business. And interestingly enough, Caterpillar now has, among other things, cooperation with First Solar on microgrids in rural villages. So that very example of how to do business in a rural area and work well with existing infrastructure that has continued to grow and actually circled back to that origin of how Caterpillar participates in today's markets, where what we're learning to do in integrating solar into the grid and go from off-grid to on-grid applications, and especially relevant in both the distribution end of the grid as well as in the transmission end of the grid. Click the slide if you would. There's reference here to some of the major innovations that took place. The ability to make piano wire in lengths on the order of 150 to 300 miles took place in the early 1980s for the automotive industry for making steel-belted radial tires. And it was the availability of wire of uniform tensile strength that enabled the creation of wire saws. So sometimes the examples of innovations that may be occurring in adjacent industries can come back and support what we're doing. The amazing properties of silicon nitride, in particular, not just for its anti-reflection properties, but for being able to hydrogenate multi-crystalline material, was discovered by folks at Kyocera. And Kyocera at the time had a joint venture working with Wacker that had pioneered not just the ability to scale making highly pure polysilicon as feedstock for growing single crystal, but had developed capabilities for casting of silicon. So Kyocera Solar, SolarX, that ultimately became BP Solar, made big strides in efficiency because of the benefits of hydrogen migrating along grain boundaries or through bulk silicon to help passivate impurities and defects within silicon. Click it once again, please. So today we have a whole host of things that we do with silicon, and I'll describe a few of those in later slides. Another click here, and one more. You can see those remote applications morphing into rural applications. Installing those telecom systems in New Guinea then brought us into rural villages, and essentially we packaged a product with a 35-watt module and a charge controller and a locally available car or truck battery preferably. And this is one of our Happy New Guinea customers from around 1982. Next slide, please. And you can see the scale goes on today. The biggest event in Arco Solar's evolution was building the first power plant for grid support. This 1 megawatt installation was completed in 1982 And off on the right-hand side of the picture, not completely visible, is a Southern California Edison substation called Lugo. This early system then was where we began to get experience with the performance both of two-axis trackers, because at Arco Solar we also had concentrating solar systems using heliostats, tracking mirrors for producing steam, helping with oil extraction. Ironically, the chairman of Southern California Edison was very passionate about seeing solar deployed by SCE, came to this Mojave Desert site to give a speech, and it boiled down to saying that his predecessors in the utility world had spent 100 years installing wire, but his successors didn't need to continue installing more wire, taking advantage of solar. Bill Gould Jr. is now the chairman of a company called Solar Reserve, based in Santa Monica. His other son, Wayne Gould, is in the investment community, investing in solar and other renewable companies. So this one man had a great influence, not just on his own family, but I would say of the leading utilities across the U.S. today, Southern California Edison ranks very highly. You can go to their website and download a white paper on how they view the role of utilities and the importance of distributed energy resources. And a lot of the executives in the utility industry are nearing retirement age right now, and at the same time as we're seeing this transformation of customer choice, being able to choose to get their own electricity from solar, and the industry needs these role models to help set examples of how utilities can successfully transition into this new world where you can put the generation close to where the load is, or can defer into the future substation upgrades or load center upgrades that are involved in the grid. On the next slide, is that learning curve extrapolated out to what might happen. We continue to see increased deployment of solar. We'll be able to get costs down below 30 cents a watt. There's the folks already today who are projecting that they can get their costs down below 30 cents a watt in the coming year or two. And we need to continue those technology innovations to not just make solar cost competitive at grid parity, but to have it be the lowest cost no matter what. So the projects that we pursue funding for through the DOE Sunshot program tie all the way back into looking at building that pipeline of innovations that have helped fuel this progress curve. On the next slide. We in the U.S. constitute about 1% of the market for solar electricity. The global average is perhaps something on the order of 2% or so. Italy, Germany, Spain have had varying times incentivized programs for encouraging the deployment of solar, helping create markets that could tie back to that learning curve, knowing that if the markets are there, the scaling will occur, the financing for the scaling will occur, and the costs can continue to decline. Japan has had an active program in solar for ever since the initial oil shocks took place and the Sunshine program was created. Go ahead to the next slide. So in looking at, if you click it again, you can see that the demand for electricity continues to grow and grow. We know that we're going to need a lot more gigawatts and find our way into the future. And part of the modeling work that goes with the projects that we carry out at DOE is to make models around not just what electricity demand will look like, but what impact increased electrification of the grid will have, increased adoption perhaps of electric vehicles or other uses of electricity. Next slide. We've seen spot situations where the projected price for power is now just under 3 cents a kilowatt hour, or $29 per megawatt hour. In our, these oftentimes are examples where government engagement in leveraging subsidies or other incentives exists, but the overall trend is steady decline in the pricing for power from PV systems, and that field performance, then the data that we have access to now from a lot of field experience gives investors a lot of confidence in the predictability of the performance of PV systems. Next slide, please. So here in the U.S., we have a rapid decline in the pricing of power plant projects. Some of the ones that are being deployed in Southern California are now being bid for capital costs on the order of $1 a watt. That usually involves a module that's around 40 cents a watt, and 60 cents is the remainder of the costs associated with that project. This year, we have projected that there'll be about 14 gigawatts of solar installed here in the U.S. Next slide, please. And one of the things that's important to gauge here is now solar and wind constitute more than half of the new energy being introduced to the grid. Some of this is for new loads, and some of this is for replacement of older plants that have been turned off, in some cases nuclear, in some cases coal plants. And in effect here, the predictability that we have, as I mentioned earlier, for both solar and wind to follow learning curves gives a lot of the industry confidence and ability to meet the commitments for those forward pricing quotes that are referenced earlier. And there's great bipartisan support for what we're doing in solar. The number of jobs that were created here, I'll speak to, but everybody likes the fact that all of the above energy approach, including solar, is within our grasp, and the lead times necessary for taking advantage of the modularity of solar give it a competitive advantage, so that a construction project isn't basically occupying capital for long periods of time while permits are being pulled or other site-related costs need to be sorted out. The next slide, please. So in the sort of breakout of where our PV systems are deployed, the utility scale systems have ramped the most rapidly, and costs have come down most swiftly, largely because you can then replicate what you're doing in the field, in a sense, having a factory in the field, installing the systems row after row in regular fashion. And the residential, the household market has continued to grow well. The commercial industrial sector hasn't grown as fast as folks had expected, but increasingly I've seen investment organizations like J.P. Morgan now beginning to take the time to understand what they might bring to the table to help these commercial uses. The property-assisted clean energy PACE financing has been particularly effective for commercial scaling. Facility managers who run a hotel, for example, are able to do off-balance sheet financing, so the owner of the building is more assured that installing renewables or energy efficiency improvements and reducing the facility operating cost is not going to have a negative impact on his monthly or quarterly earnings statement. And the next slide, please. We are very excited that it looks like the tally of solar jobs across the U.S. is something on the order of 260,000 at this point in time. And if you look at this slide, broken out items that we export, we're a big material exporter, especially polysilicon and materials like Tedlar. And on the right 3/4 of the slide here, what we do here in country and using our own equipment, the majority of those 260,000 jobs, 170,000 jobs are related to developers and installers. Installer jobs pay well. They're on the order of $20 to $25 an hour. Working in a factory here in the U.S., wage rates tend to be on the order of $10 to perhaps $15 an hour. So we have created a massive number of jobs in a short amount of time. Part of the reason that I was keen to speak today is that it's very important that we have a pipeline of talent to fuel this continued growth in our industry all the way across the value chain, whether it's in the high-tech dimension, the financial services dimension, or jobs that relate to maintaining systems that are out in the field as we increase every year the number that are deployed. In a sense, building a module-making fab is a fab that makes power plants. So each year, a fab today, a typical large-scale production facility is on the order of 1 to 3 gigawatts in size. So that fab cranks out a power plant of 1 to 3 gigawatts in size every year. So once we've made the investment in that capital equipment, it's one that continues to serve for a long period of time. The next slide. R&D drives a large portion of what we do. Tracked here are some of the sort of major material classes from the chart that NREL regularly publishes. And if you click one more time, much of the kind of thing that we do in the Department of Energy is to work on ways to continue to advance efficiency, just as a vignette here, what's happened with multi-junction materials and the number of records that have been set in that category bodes well. And on the next slide, while we know that things change rapidly, the adoption and commercialization of technology takes time. Most of the manufacturers of silicon solar modules are transitioning to a passivated emitter rear contact design the invention of which goes all the way back to 1983. There you can see a young Martin Green sitting in the foreground, Andrew Blaker, Stuart Winham in the background there. Folks, Bruce Godfrey there on the right, who went on to form his own company making instruments. This is sort of to maintain our humility, I suppose. It takes a long time to work at understanding how to scale the technology, how to have a tool that can handle 4,500 wafers per hour, handle the wafers consistently every hour of every day is no simple task, and is much of the skill set that has enabled the scaling. And having a durable contact system and a durable package has been a great benefit to the ability of the industry to scale and not have the fundamental underpinnings that are associated with manufacturing move around. The next slide. This is a waterfall chart of what we do in Sunshot today. The original Sunshot was launched in 2011 with a goal of getting to 6 cents a kilowatt hour. We're at 7 cents now, so we're 90% of the way towards the goal that we had set for 2020. So when I arrived at DOE, we spent some time to update our targets to cut that in half again, to look at what we could do to get to 3 cents a kilowatt hour. A lot of the great modeling work that Mike Woodhouse, Robert Margolis, Dave Feldman have done at NREL enabled us to put together a series of charts. What are the dials, whether they're efficiency, durability, automation, and that can get us to that 3 cent goal. And sort of bounded here on this chart on the sort of the 2016 benchmark, a key thing I'll highlight here is that this now assumes single axis tracking. The initial Sunshot program, single axis tracking hadn't matured the way that it has over the past half dozen years. And so that has also helped energy harvest a lot. If you look closely at this figure at the top, that 7 cents today would be about 10 cents in Seattle, which is less sunny than Kansas City, which is our reference site for that 7 cent target. And the sunniest part of the U.S., Daggett, California, in the Mojave Desert, the high desert of Southern California, not far from where Edwards Air Force Base is located, forms that lower bound on the cost per kilowatt. Let's go to the next slide. We have similar projections and sort of a record of our history in Sunshot for commercial scale and residential scale systems. So for each of these market categories, there are a set of targets that relate back to things that we use as our roadmap to guide allocation of funds and priorities of funding. On the next slide. There are a lot of different trade-offs that can be made. You can trade off efficiency, module price. This is a set of ISO LCOE curves, constant LCOE at 3 cents a kilowatt hour. A big lever here is the weighted average cost of capital. If people have greater confidence in the long-term performance of a system, it's possible to borrow money to capitalize a project at a lower interest rate. There are ancillary benefits for improving life as well. Typically today, a lot of the more recently manufactured modules in sampling work that Sarah Kurtz, John Hogelmuth have done in their role at NREL, we see something that's in the ballpark of about 0.2 to 0.3% per year degradation. The next slide. What we've modeled here, one of the benefits of getting to a position where we cut the cost in half is we're able to move from this green line, baseline, which is more or less a projection of the increased adoption of solar if we only got to 6 cents a kilowatt hour. And you can see that by 2030, it would represent something on the order of 7% of the U.S. electricity needs compared to today. And we've put in scenarios around 2, 3, and 4 cents a kilowatt hour. Getting those costs down cause a step function in the increased market penetration we could have. And the dotted lines represent even further increases in market adoption that could go with low-cost storage. So all of these elements come into play in looking at the modeling for how we can affect the use and scaling of solar. The next slide, please. This map overlays for folks who want to get a sense of the correlation between how much sunlight there is and what LCOE levels we could get to where we are today and where we project getting to in 2030. The next slide. Much of what's important now is the merging of energy and information. So the adoption of solar into the grid is key to continuing that decline, the scaling of manufacturing. So in our solar group, we pursue photovoltaics, we pursue concentrating solar, and we have a system integration team that works at ways that facilitate the use of information. Most the module level power electronics today has Bluetooth connectivity that enables people to track the performance of modules, and in some cases individual strings in a module. And that information can be useful all the way up to the operator of a transmission grid in being able to manage the system voltage and system frequency. And some of the inverters that are now commercially deployed essentially could perform services 24/7 because even though they might not be used to convert DC to AC electricity, they can be relevant to stabilizing the voltage and frequency response. And early tests in California look like the response time may even be better than that of spinning reserves that are often always kept online should a major fossil-fired generator source have to be taken offline. Next slide. A lot of the modeling that's been done enables the use of mapping materials, Google Earth, or similar mapping tools that can enable an installer to look at a location without needing to travel there, can get first-order dimensions, can run optimization models for how best to configure strings in the available roof space. The next slide. There are, keep clicking a few times, there are a number of players here who have leveraged this Google Earth capability. This is just a representative mapping you can find in Google Earth where the existing power plant infrastructure is observable, and can be used by utility planners, public utility commissions that states have for managing the utility monopolies that exist. In the U.S., we have over 3,800 different utilities, and we have over 18,000 authorities having jurisdiction. And AHJ is one of the most important people involved now in the value chain of getting solar deployed in rooftop systems, residential as well as commercial. On the next slide. We've worked a number of projects to tie forecasting tools. We work with IBM, for example, being able to utilize machine learning that can help match the upcoming weather projections with the identification of load centers that the transmission or distribution utility would like to manage better, and enable greater deployment of solar into the grid, essentially making better use of the wires that we already have. In a typical utility site, there will be over 40% of the capital is tied up in wire and rights of way. In a sense, this is a Uberization of our grid that's happening, where the ability to deploy solar where it's needed and match up where various energy resources are needed, becoming far easier because of that interconnection of information that goes with our generation. The next slide, please. You can go online. One fun thing to do is to look at the Energy Sage website. And there, as an example of something we've supported at Sunshot and DOE, a person can enter their zip code. It will give them a sense of what the benefits are associated with putting solar in their roof, and will provide links to a number of installers that can compete for that job if they choose to go ahead and install solar. The next slide. So the overarching picture here is of a grid that looks somewhat like this. There are new, increasing large-scale generation sources, solar upwards of 700-800 megawatt systems being the largest power plants. Those are systems that are more or less on the same scale as a coal-burning power plant, to give everybody a calibration. But the action that's happening down on the distribution end is where a lot of the excitement exists. Being able to have the wires serve two-way energy flow supports the adoption of a stronger grid system, because the system has local islands that are not dependent on a single backbone. And the microgrid capabilities, the kind of thing Caterpillar Solar is doing in rural villages, apply just as much to Palo Alto municipal utilities' use of microgrids. And a lot of the home energy automation software further reinforces the ability to make use of energy efficiency approaches. All of this in an envelope of information that is provided by way of having internet capability, which then opens up energy markets. So consumer behavior begins to change as a result of time of day and value pricing of energy. And we also work with the Office of Electricity at the Department of Energy in assuring cyber secure systems come along with this increasingly robust and resilient grid that happens because of the expansion of solar. I think, John, that I'll stop there. I realize that used up my hour here. But I'm happy to, maybe we can compile some of the questions, or if folks have questions they want to bring forward. I'm happy to do what I can to respond to questions. And I look forward, as I say, to getting a chance to meet you. You're welcome at Sunshot in Washington anytime. And if you do get to town, please make a point of visiting the solar exhibition at the Smithsonian. I'll wrap it up here then, John.
Comments or it looks like questions that are in the chat window now. Would you like me to read them to you, or I'm not sure if you can see them, or?
It would be helpful if we could take a couple of questions, if you can pick a couple that you'd like to highlight here.
Yeah, absolutely. Well, one of the comments from Angus Rocket was that on an earlier slide, when you showed a cost curve, there was a he had just wanted to note the cadmium telluride, and I guess in its importance in affecting the cost reduction in solar in the U.S. in the last number of years. But in terms of a question, sorry. Well, I was going to just say, in terms of a question, there was one regarding the DOE R&D and how much that was broken down by national lab research versus university grants and things of that nature.
Roughly speaking, currently our annual budget is on the order of $200 million. About 38% of that goes to national labs, a large portion of it to NREL, but significant portions to Sandia, Pacific Northwest Labs, Lawrence Berkeley Lab, Lawrence Livermore. This grid modernization work that we do is joint between the solar group and the Office of Electricity. The solar group is in a collection of activities called Renewable Power. So my colleagues are in water, wind, and geothermal. And then we as a group are reporting into the head of energy efficiency and renewable energy in the DOE. The parallel group in the Office of Electricity has historically attended to grid initiatives. And part of the reason I joined DOE was to help connect the dots between different parts of the organization now that solar and wind are at the scale they are. Our funding to universities, as best as I recall right now, and you can check me on this, is about 18% of our funding level. It fluctuates a bit from year to year, but that gives a first-order feel for the level of where the money is allocated by broad brush category.
Two other questions that have come in. One is in regards to energy storage, and you know, what research or plans that DOE has in regards to that.
DOE does have storage initiatives. They're mostly associated with the Office of Electricity. In the solar Sunshot team, we do not have storage per se. We have some examples of partners that are involved in integrating storage with solar, but the work on batteries principally today is in the vehicles program. I don't know exactly off the top of my head, but I think roughly speaking, there may be as much as $180 million a year spent on battery technologies, most of that at Argonne National Lab in Chicago. And the Office of Advanced Manufacturing works on high-speed roll-to-roll coding capabilities and the like. And one of the thoughts that has occurred to me is that the ability to take advantage of the experience we've had in thin film coating large areas at high speeds, uniform lathe with minimal pinhole defects might find a way to bring the best, somewhat analogous to the steel belted radial tire story here, where tools for roll-to-roll coating are moving along, a lot of it for power applications in battery storage for getting torque to the wheels in a car, as opposed to energy storage emphasis. So it could be that the costs decline for the ability to coat large areas uniformly for the power application, and the tool, the equipment itself for doing roll-to-roll coating could enable approaches, say with lithium titanate or some of the spinels, that would be better suited to a storage use and energy use as opposed to a power use in a battery. The Office of Electricity works with some battery technologies, but also with pumped hydro approaches, compressed air approaches, flow battery approaches, a wide variety of potential leveraging storage technologies that could help expand the adoption of solar.
There's only currently one other question, and this might be a little bit more nuanced. Someone was curious if you had any information regarding the new administration's plans for R&D.
No, essentially at the moment there are about 20 people from the new administration who are occupying office space in the Forstall building, the DOE headquarters. A number from the transition team, a team that has come to study what we do. Their involvement is really pending the confirmation of Governor Perry as Secretary of Energy. I think the Republican have a sort of off-site session planned for the latter half of this week. So I don't anticipate the confirmation hearing coming to closure in a vote perhaps until sometime next week. By next week, we expect that there may be as many as 40 people from the new administration who sort of awaiting Governor Perry's, or Secretary Perry's, if he's approved, guidance as to what roles they may play in the department. Long-winded way
Great.
of saying
Understandable. There was one other question that just came in. If you've got time for another, this was regarding the question was regarding if there was a drastic reduction in cost for silicon material, how would that affect the cost of the installed?
Not much. So if you picked a benchmark of where modules are selling today, around 40 cents a watt, in the ballpark of 6 to 7 cents a watt is about where the silicon piece is, and the scaling of silicon as it essentially in 2004 more silicon, something on the order of maybe 60 to 80,000 tons per year of hyperpure silicon was used by the integrated circuit world. Today, the solar universe consumes, I don't recall exactly, but something in the ballpark of 300,000 tons of silicon. And the cash cost, the unburdened cost of production of silicon generally is below about $12 a kilogram. It had been at a high selling price of over $300 a kilogram in 2006 and 2007, when the supply of silicon that was essentially the overflow from the IC world then became too little to keep up with the demand for silicon. But additional silicon capacity has come online. A lot of the reactors for scaling of the production of polysilicon from trichlorosilane feedstocks. Those tools were sold by a company in New Hampshire called GT Equipment.
Okay. Before we let Dr. Gay go, does anyone else have any final questions? James, there will be a, we've been recording the presentation, and there will be a posting of it on our YouTube channel. That link will be updated on our website, nextgenpv.org, and distributed through our social media channels. If you'd like to look at previous presentations in this lecture series, they are currently on our YouTube channel. Okay. Well, thank you again, Dr. Gay, for taking the time to give this really excellent presentation. And please, if you're ever interested in participating again, let us know, and we will definitely have you come speak again.
It would be my pleasure, John, and thank you all. Really appreciate the opportunity of at least getting acquainted remotely here. Hope that the background noise didn't create too much of a distraction, but thank you again.
Oh, no, please, thank you, and no problems with the background noise. Thanks again, everyone, for attending, and this is an ongoing series that generally is every 2 weeks. We kind of have them on occasion a little less regularly, but if you're interested in tuning into future solar presentations, keep an eye on our social media channels. Thanks again, everyone.
Thank you. Thanks.